Exam 4 is going to be on acids and bases, chapter 14 and chapter 15. Today, I'm just going to try to cover chapter 14 because it's the biggest slide set. Next Thursday, we'll have time to finish chapter 15 and also talk about the upcoming lab. We won't have a lab on this Thursday. It'll be the following Thursday, but that'll give us an opportunity on Thursday during the lab time to discuss Le Chatelier's principle and the lab that we're going to do the following week. So, chapter 14, acids and bases. Right. Historically speaking, acids and bases were understood based upon the effect that they had. In other words, we knew that acids gave you a sour taste, bases gave you a bitter taste, and that's why most medicines. There's Jada. Most medicines are basic. There are a few that are acidic, but most are basic, and they're encapsulated so that you can get them past your tongue before you get that bitter taste. They get into your stomach before they dissolve. If you ever bite into most drugs, if you just bite into the capsule, you're going to get a bitter taste. They're basic. But the modern scientists wanted to understand what caused that. And one of the first plausible explanations was proposed by Arrhenius. You'll remember Arrhenius from chemical kinetics, same person. Arrhenius said that acids in aqueous solution produce hydrogen ions from their molecule. That means we're expecting to see a hydrogen in that molecule that can be dislodged from the molecule and go into solution. So examples would be like hydrochloric acid or nitric acid. Right? Those hydrogens can be they can be ionized from these molecules into solution. Bases, according to Arrhenius, produce hydroxyl ions from their molecule. Okay, so examples of that would be sodium hydroxide, right? Potassium hydroxide, magnesium hydroxide. Any one of those, when you put them in aqueous solution, they will produce hydroxide ions from their molecules. And this is a good explanation for probably over 90% of acids and bases that you'll encounter in the natural world. But there were limitations. And eventually, there were examples of acids and bases that didn't fit this explanation. Notably, we had ammonia in aqueous solution exhibits basic qualities, right? There's no hydroxyl in that molecule. So we needed a better explanation. This was still believed to be the case. You had to have an excess of hydroxides in solution in order to produce the basic effect. And Bronsted and Lowry, who worked independently, were accepting this explanation for basic behavior, but they needed a better explanation. So they said, we've got a different definition. And what happens with ammonia is when you put it in water, oops, too small. When you put ammonia in water, that what you get is a transfer of one proton from this water molecule over here. And that produces the ammonium ion plus hydroxyl ions. Okay, so the explanation that Bronsted and Lowry came up with independently was that acids and bases should be viewed in terms of proton movement, not hydroxide availability. So in this case, we would say this is our base because it accepts a proton or a hydrogen ion. Whereas this water serves as the acid because it donates a proton. So the Bronsted-Lowry definition is based upon proton movement. Acids donate protons, bases accept protons. And this works for 99.999% of the rest of all the acids and bases. Okay, so here's an example. Now, in many cases, the acids will fit both Arrhenius definition and Bronsted-Lowry definition. In our example here, hydrogen chloride in aqueous solution reacts with water and produces chloride ions plus the hydronium ion. Now that hydronium ion, let's see. Is the product of the proton transfer. Now, in actuality, what happens in solution is that the proton is transferred. Protons, hydrogen ions, never exist as free-floating ions. They just don't do it, not in the real world. They are transferred. So when we transfer a proton from hydrogen chloride to a water molecule, we get the hydronium polyatomic ion. Now that's reality. For calculation purposes, sometimes we can simplify our reaction calculations with the protons as a separate entity, but recognizing that that doesn't happen in the real world. It's only valuable for calculation purposes. And I'll show you examples in a few minutes. Okay. So this is an animation of what happens when ammonia on the left, the blue is nitrogen and the lighter colors are hydrogens, comes in contact with water. There's sort of a tug of war. And if the ammonia wins, it takes that proton away from water molecule and leaves behind the hydroxide. So if we look at it in terms of the Lewis dot structure, remember water looks like this. That if we break that bond, Where do the electrons go? Well, in this scenario, the electrons all go here. And that means this proton now, this hydrogen ion, is missing an electron. And remember, hydrogen is like this, like that, neutral. If we remove an electron, we get a hydrogen ion. Now it has no electrons and one proton. So if we send both of these electrons pair to oxygen, then this hydrogen comes out as a hydrogen ion. Let's see, who's that? Or somebody drop out and come back. I think that happened, yeah. Oh, no, Ann's here. Okay. So I'm going to erase this and make more room. Um, and semantics. Let's see, I need to go back up here. Yep. When let's say acids, okay, an acid, this is a covalent bond. Okay. So when the bond breaks, we say the process is ionization. All right. If we have a base which does have a hydroxyl in its molecule, like sodium hydroxide, this is an ionic bond. So this is called dissociation. Because all we have to do is separate those two ions. They dissociate from one another. But for this one, we have to produce an ion as a product of the bond breaking. That's semantics. In this case, we're showing two water molecules, right? They're having a tug of war, right? And that can happen. If you have pure water, then you can have a water molecule here and a water molecule here, and you can transfer a proton to this molecule, and that will give you an ionization product. Okay? You create a hydronium ion and a hydroxyl ion. That does happen. Now, when we let's talk about these in generic terms first. Right, we learned in the first semester how to identify an acid for naming purposes. An acid it starts with a hydrogen, right? Starts with a hydrogen, at least one, sometimes two, sometimes three. But in our illustration, we're just going to do a monoprotic acid. And then when we put it in solution, it has the opportunity to react with water. And if it does and transfers that proton here, then we get what's left over plus the hydronium ion. Okay? Terminology. According to Bronsted and Lowry, the proton donor is an acid. And the proton acceptor is a base. Those are the reactants. On the product side, what do we produce? the acid produces a conjugate base. That means this species right here can accept a proton from somewhere. In this scenario, it might accept a proton from that one and go back the other direction, right? We know that we can go forwards and backwards. That makes this one, let's clean this up a little bit. Okay. This one is the conjugate acid. Okay. So that's terminology. An acid in this reaction produces a conjugate base, and the base produces a conjugate acid. Now, notice one thing about this reaction. We only have one proton here, so it can only transfer one proton. But say we had something with two protons, like that. These reactions occur. Oop, there's the other Haley. Oh, no. Wait a minute. Must have dropped off and come back in.
I did. My cat walked across the computer and turned the Wi-Fi off on my computer.
Okay. Okay, back to our topic. If you have a diprotic acid, these reactions occur one proton at a time. So when you're asked to write an acid-base reaction, you need to read the problem so that you understand, are they trying to get at a single proton transfer, or do they want an overall reaction like we would do in a titration? But what actually happens is one proton at a time. So that means on this side, we would get this anion and this hydronium ion, right? And then this one can also undergo a proton transfer with another water molecule and give us that deprotonated ion plus another hydronium. So what I'm trying to illustrate here is that these reactions in reality occur one proton at a time. And we studied equilibrium in the last chapter. These equilibrium expressions for these reactions are independent of one another. In other words, this one will have a K for the acid dissociation first one. This one will have a K for the acid dissociation second one. These will be two separate numbers. Now, of course, we can combine them, just like we did in several problems, to find out what the overall is, but each reaction has its own K. All right. Now, for chemical definitions. In popular media, most people who've never studied chemistry think that call strong and weak according to its physiological effect. So if you get a burn from an acid on your hand, they say that's a strong acid. In chemical terms, the definition of a strong acid is in terms of its equilibrium. So the equilibrium for a strong acid lies far to the right. In other words, when we say this, and I'm going to write it, this is in the abbreviated form. This is not reality, but it helps us with calculations later. You can go this way, like that, and this equilibrium lies far to the right. That means it's a strong acid. Now, it may be very dilute. You can predetermine the concentration yourself when you produce this solution, and it can be very dilute. But the acid itself is a strong acid because it dissociates. It ionizes completely to one side. The other thing we have to recognize is this strong acid. Strong acids always produce weak conjugate base. Okay? And that makes sense because the strong acid wants to completely ionize. So what does that mean about this one when it tries to go back the other direction? Well, if the equilibrium is this way, it's not interested in acquiring a proton from anywhere, right? So that makes it a weak base. According to Bronsted and Lowry, it's a weak proton acceptor. Whereas if we had a weak acid like acetic acid, like that, then when it dissociates to produce these products, right? That's aqueous. Acetic acid produces hydrogen ions, which we know would be attached to a water molecule, and the acetate polyatomic ion. If this is a weak acid, it produces a strong conjugate base because the equilibrium lies way back over here. That means that it's looking for protons, and wherever it finds them, it's gonna pick them up and go back over here. That's the definition of weak and strong in chemical terms. Now, you can have a weak acid that is very highly concentrated, and it will be corrosive. It will have a damaging effect on your tissues. We used to use glacial acetic acid, which is 100%, right? Very dangerous. It's a weak acid, yes, but it's so concentrated it can do damage to your skin like that. As a side, the other possibility is this is an organic acid. If you combine it with an oxidizing acid or a strong oxidizer of any kind, you're going to get an exothermic reaction, very violent exothermic reaction. And it could, in fact, set it on fire if there's oxygen around. So that speaks to proper storage of your acids and bases. Right? You don't want to store one of these. You don't want to store this with this, which is about 70%, or this, which is about 98%. Those two will react with this and produce an explosion. Okay, back to our topics here. This is just an artist's representation of what a weak and a strong acid are. Strong acid completely dissociates, right? So the K value will essentially be infinity. But the weak acid will have a value that's much less than 1 because reactants are favored. Okay, so this table, which comes out of your textbook, summarizes what we discussed so far. There we go. Okay. Now, I drew you a picture earlier and mentioned the fact that water, pure water, will react with itself. One term that we can use there is autoionization. Autoionization works for any material that has protons. So water can autoionize, transfer a proton from one water molecule to another. Ammonia can autoionize and transfer a proton from one ammonia to the other and produce the ammonium polyatomic ion and the azonide, they call it the azonide ion, NH2 minus. This is autoionization. It can happen. Now, you're not likely to find pure ammonia. We call it anhydrous ammonia. It's not commonly available except for agricultural purposes. Farmers that have large acreages and they need lots of nitrogen fertilizer. For instance, corn growers. Corn takes a huge amount of nitrogen to grow. And it's more efficient to deliver that nitrogen in as concentrated a form as possible. And one of the ways they do it is anhydrous ammonia. It takes special equipment. Everything has to be stainless steel that comes into contact with the ammonia. And you have to have stainless steel knives that go down into the soil and they inject the ammonia into the soil, deep into the soil. Because ammonia at atmospheric conditions, room temperature, will vaporize like that. So you want to get it down there and into the moisture when it can react with water and it stays put. But the process that ammonia undergoes while it's in the tank is autoionization. Another term that's applied here also is called amphoteric. An amphoteric substance is like water, can act as an acid or a base. And that's where we drew the reaction where we had water reacting with water. Right? And it's in equilibrium with these two ions. Let's see, that's aqueous, and this is aqueous. Okay? So that's an amphoteric nature of water. Sometimes we call it amphiprotic. Ampho means both. It's the Greek prefix that means both. So it can either be an acid or a base. Now, at 25 degrees Celsius, 25 degrees C, the equilibrium constant for this expression, we give it a W. The W is reserved for water only. This KW, we would normally put the concentration of hydronium times the concentration of hydroxyl divided by the concentration of water squared. But notice water is a pure liquid, and we don't put pure liquids in the equilibrium expression. We don't put solids there either. So the equilibrium expression for this reaction is simply the hydronium times the hydroxyl. Okay? And that value is 1 times 10 to the minus 14. That means that the equilibrium lies way over here. You get very little of this in pure water. Now, you can put other things in water and change its behavior. But one thing we have to remember, keep in the back of your mind, is no matter what we put in the water, acids, bases, salts of any kind, this is always acting. It's always working. You always have this as a possible reaction. A water molecule encounters another water molecule in an acidic solution of hydrogen chloride. When they encounter, they undergo this reaction. Right? So this reaction always happens no matter what else is going on in the aqueous solution. Now, if you put something in water that produces hydrogen ions or hydronium ions, that is a stronger acid, then this may become insignificant in terms of your calculations. Right? So you just have to compare the reactions of the two, for instance, and say, all right, which one is dominant? Okay, moving on. Okay, now we have three possible situations when we produce a solution. If it's pure water, then we know that these two are going to be exactly equal. Why? Because they're produced from here, and it's a one-to-one relationship. So the same amount of this that we produce the same amount of hydroxide. That means that these will be equal. And if equal, and we're going to use the abbreviated form here, if that value equals this value, then we have a neutral solution. Neutral in terms of acidity or basicity. In other words, it does not exhibit either acid or base characteristics, either one. It's neutral. Okay? The next definition is if this concentration exceeds this concentration. Then we have acidic conditions. Okay? And we flip the coin the other direction. If this concentration is less than this one, then we have basic. Now, can we get acidic or basic conditions from pure water? No, we can't. Oops, go backwards. You can't. You have to do something to modify the solution. You have to add something to it, either to go this way or that way. If we add hydrogen chloride to the solution, we will cause an imbalance for the hydrogen ions. If we add sodium hydroxide to the solution, we will imbalance toward the basic. Okay? But whatever we do, this still works. So if we cause this to increase, then this one has to decrease in order to maintain this equilibrium. If we make that one go up, this one has to go down. And we're going to use that to our advantage when we do calculations concerning acid-base equilibrium. Okay. Now, how did I get that? I saw Ann's name attached to this line that's drawn here, but I don't know how to get rid of it. Maybe stop the share and start again. Let's try that, because I don't want that to be recorded on every slide. Let's share again. Okay. Okay, it's gone now. All right. So we can write an equilibrium expression for any acid. We've got a generic acid here. Let's take acetic acid. Just use that as a real example. So we've got acetic acid, right? Aqueous solution, and it's going to transfer a proton to water, and it's in equilibrium with the, it's in equilibrium with the hydronium ion and the acetate ion. Oops. Let's try that again. 8, 3, 2 minus. Okay. So our equilibrium expression here, the Ka for this one, and it only has one Ka because there's only one proton there. These hydrogen atoms are so tightly bound, they will not ionize. This is the only one. So the Ka expression for this would be the hydronium ions concentration, the acetate ion concentration, divided by the acetic acid concentration. Okay. So you can use hydronium in here, or you can write it a more simplified version that removes the water and simply turns that into a hydrogen ion, and you get the same calculation. Sometimes it's easier to do it that way. So that's the equilibrium constant expression for this acid. And all we need to know is at equilibrium, what is this concentration, what's that concentration, and what's this concentration. Notice we don't put water in there because it's a pure liquid. Its concentration doesn't change. All right, so if the equilibrium lies to the right, this Ka should be very large, right? Much greater than 1. And if the equilibrium constant is, if the equilibrium lies to the left, the constant should be small, much less than 1. Just like we studied in chapter 13. So eventually we're going to get to use ice tables for these reactions too. I hope you see that coming. All right. Let's say this is a weak acid, right? That makes this a strong conjugate base. In this case, water is a very weak acid. So that makes this a strong conjugate base. Or this is a weak base, that makes this a strong conjugate acid. If water is a better base than this one right here, do products or reactants dominate? For this particular reaction, okay, let's focus on the one that's given. HA is an acid. Now, compare it to the water right next to it. If water is a better base than A minus, what does that mean? Bases accept protons, right? Does that HA want to accept a proton, or does the A minus want to accept a proton? The A minus wants to accept a proton. So we should see favored, excuse me. Does that mean that HA is a strong acid or a weak acid? Well, if water is a better base than A minus, then water accepts protons less readily than A minus. That's what we're saying. If water is a better base than A minus, then water wants to accept a proton better than A minus. So that means HA has to be A minus, then would be a weaker base than water, and that would make HA a strong acid. Now, how about the value of Ka? Is it greater or less than 1? Well, if HA is a strong acid, products are going to be favored, which means the K is going to be greater than 1. All right. So let's look at this example. If we have 1 molar solution of hydrogen chloride in water, let's look at these in terms of the strongest to weakest base. All right, I'm gonna have to erase some of this now. Let's just clear the board. Okay. So we've got these possibilities. We're trying to order them. A minus, and A minus is aqueous solution from a weak acid. From a weak HA, a weak acid. What does that mean? That means this is a very strong base. And then the chloride, we know where chloride comes from. Chloride is from strong acid, strong HCl. So when given this, put things in order, I like to nail down the front and the back. Right? So which one is going to be the weakest base? That one right there. From the strong acid, this is going to be the weakest, strongest to weakest. So we're going to put chloride over here. Right? It's going to be the weakest. What's going to be the strongest? Strongest is going to be that one. From a weak acid, it's going to be the strongest. That puts water in the middle. So we should have A minus, water, and chloride. Okay. Okay. There's another scenario. Suppose we want to put the conjugate base in solution, but we don't want to put it in there from the original acid. We want the conjugate base, but we don't want its acid to go along with it. We don't want the hydrogen. So how would you do that? Well, you need a soluble compound with the A in there. We know that all sodium salts are going to dissociate completely in aqueous solution. So this will produce A minus in aqueous solution. And sodium will be a spectator. It won't have anything to do with the reaction. Now we know that this is, and we're told that A minus is from a weak acid. So this is a strong base. Okay, that's given. Now what happens when you put it in aqueous solution? Well, it dissociates from the sodium. And then, since it's a strong base, it goes looking for protons. Okay? And the only thing available is water. So it's going to take a proton from here. It's going to produce this weak acid. And what's left over? The conjugate base of that water as an acid. So which way will the equilibrium lie? If this is a very strong base, it's going to drive the reaction to the right. It's taking protons from that water. We're going to see the equilibrium lie far to the right. Nope, sorry. I left that in there on purpose. The creators of this slide set got that one wrong, so I had to correct it. Okay. Let's see. Is the value of KB greater than or less than 1? What would the KB be? We know how to write the KA, but here we have a situation where we're going to write the KB for that base. So we need weak acid concentration. We need the hydroxyl concentration. And we need the base concentration. And we don't include water because it's a liquid. So that's your expression for Kb. All right. Which way will it go? If it's going to be heavy on that side, right? Large numerator, small denominator, this is going to be greater than 1. Okay? All right. Well, say we weren't told, we're not told that A minus is a strong base from a weak acid. But all we have is the expression of Kb, this expression, and we have a value out here that's greater than 1. That tells us that A minus is a strong base. So we can look at it 2 ways. We can come at it from this side, or we can come at it from this side and deduce that this is a strong base. Okay. Let's try another concept check. See if we've got these ideas firmly in hand. We've got acetic acid. We've got hydrocyanic acid. They're both weak acids, but acetic acid is stronger than hydrocyanic. So the question is, arrange the following from weakest to strongest as a base. Okay, proton acceptor. So let's say if we have acetic acid, C2H3O2, I'm going to simplify it. We're just going to do this. And C2H3O2 minus, recognizing that these are all aqueous solutions. Right? Just simplify it. And then we can do the same thing for hydrocyanic acid. Oops, yeah, Cn minus. Okay. So this is going to have a K value, Ka for acetic acid, and we're going to have a Ka for hydrocyanic acid. And then we also have this one, right? We got the chloride, so it must have come from this reaction right here. And its K is equal to infinity because it's a strong acid. And then there's water, right? So water would simply be like this, simplified version. Okay. And we know that the Kw here is 10 to the minus 14. Okay. Arrange these bases from weakest to strongest. All right. So in order to make that, in order to deduce the arrangement of bases, we need to know something about the acids. This is an extremely weak acid. Weak. That makes this an extremely, hydroxyl's not in there. So this is a weak acid. It's also a weak base, right? Because water with water, they don't want to transfer protons at all. So one water doesn't want to give it up and the other water doesn't want to accept it. So this is a very weak base also. All right. What does that make this one? That makes this one very weak also. How about these two? if this is a weak acid, and this is a weak acid, and this one is a weaker acid than this weak acid, that makes this one a stronger base. A stronger base than this one. Okay? So the question is competition between this weak base and that, no, strong base. Competition is between these two. Which one is the strongest base? Well, if this is a weaker acid than that one, then this is a stronger base. So the strongest base is probably a cyanide ion. Okay. How about the weakest base? Took care of this one. How about the weakest base? Well, the weakest base is going to be this one right here. Chloride. Now what we have to do is say, what's the relationship of this one to this one? And I think that this one is a stronger base than water. So we would put, this one would be acetate. Acetate ion, and then water. So let's see if I'm right. All right. We know the Kw for water is 10 to the minus 14, which makes it a very, very, very weak base. But the Ka for acetic acid is 10 to the minus 5. And the Ka for hydrocyanic is 10 to the minus 10, which means that justifies saying this is a stronger base than that one because this is a weaker acid than that one. So cyanide's the strongest, acetate's the next, water, and then chloride. Now, we weren't given those values. We knew Kw already. We didn't know Ka for acetic acid and the Ka for hydrocyanic, but we were given relationships of these two. So we deduced from that. These numbers just confirm it for us. Okay. Next problem. Suppose we're going to have a reaction. Hydrocyanic acid reacts with the fluoride ion to produce cyanide ions plus hydrofluoric acid. Right? We want to know what's the K for this reaction. Right? Now, instead of just putting an acid or a base into water, we've got a reaction of two, an acid and a conjugate base of an acid. And we're given the Ka for each one. We want to know, is the K greater than 1, less than 1, or equal to 1? In other words, which way is the equilibrium? I think I've got an explanation here, so I won't have to write it on the board. All right, so there's your reaction. There's the Ka for HCN and the Ka for HF. But notice HF is on the wrong side for the Ka expression. What does each Ka mean? All right, for Ka of HCN is very small. That means there's a drive for it to remain as HCN on the left-hand side, right? So there's the drive. So what we have to do is compare that to the drive for HF. Does HF want to be on one side or the other? HF is small, so there's a strong drive for HF to remain as HF. Okay, who's going to win? Who's got the stronger drive to remain as the unionized acid? Well, the one with the smaller Ka is going to have the strongest drive to remain as the unionized. So that means that Hn is a smaller value. Ka for Hn is a smaller value than the Ka for Hf, which means that we should expect the reaction to remain on the reactant side. Okay? HCN wins this battle, driving the reaction toward HCN and toward reactants. All right, so the overall K, since the reactants are favored, the overall K should be less than 1, much less than 1. Okay, that's the qualitative reasoning, semi-quantitative reasoning to determine which side the reaction is going to go. All right, now, suppose we have a weak acid, and we have the Ka for the weak acid, but instead of the acid being part of the reaction, the conjugate base is part of the reaction. Say we have this weak acid, and it produces that and that, and this part right here is delivered into the reaction like that. Maybe it's sodium salt, right? And we want to know, we know what the Ka is for this reaction. We want to know what is the Kb. Okay? So here's how you determine the Kb if you know the Ka for the acid. You want the Kb for the conjugate base. Right here. All right, here's the reasoning. This is a simplified version of the ionization of Ha, and there's the expression for Ka. All right, here's the reaction that you would experience from that. If you just put that conjugate base into aqueous solution, not as the acid, but simply as the conjugate base, then this is the reaction that you would get. And its Kb looks like that. Okay? If you add those two together, what do you get? The HAs cancel, conjugate bases cancel, and you're left with the dissociation of water. Okay? So what's the expression for water? Well, we've just added Ka plus Kb, and there's that box again. So what that gives us is Ka times Kb equals Kw. All right. So if we solve for Kb, that's Kw divided by Ka. That's how you calculate Kb from Ka. You simply divide it into Kw, and that gives you Kb for the conjugate base of your weak acid. All right. You can go both directions too. If you have the Kb and you want to find the Ka, you just divide Kb into Kw. Either way works. The mistake that students sometimes make is they think that Kb is the reciprocal of Ka. That's not the case. We just proved it. Okay, now if we want to calculate the K for this reaction since we're reacting the hydrocyanic acid with the conjugate base of hydrofluoric acid, in order to add two equations together and get that whole one, right, we're going to use Hess's law. We're going to need to know the Ka for hydrocyanic acid, and we're going to need to know the Kb for the fluoride ion. Here we go. So these are the competing reactions. There's the K for the hydrocyanic. We know that to be 10 to the minus 10th. This one is for the HF, but it needs to be reversed. So if we, right, in this case, we're not going to have to calculate Kb because we have the expression, and what we need to do is invert the expression, which will actually be the inverse of that K value. Then we can add them together on the next slide. Okay, when we add them together, we get this expression, and then all we have to do is multiply those two values together, and we get the K for the reaction. 8.6 times 10 to the minus 7. All right, let's talk about pH. Many of you have had biology or anatomy and physiology, and you've been introduced to the concept of pH. This is the chemical explanation for pH. pH is nothing but a mathematical transformation of hydrogen ion concentration. So this was developed by a Swedish man, Sorensen, who was working with concentrations of hydrogen ions where he had to use scientific notation. And scientific notation, when you have to do lots of calculations and lots of measurements, is a real pain. So he proposed a simpler version. If you take the hydrogen ion concentration and just take the log of it, that converts it to a decimal number, a manageable number, right? But with when you have 10 to the minus something here, your log is going to be a negative number, right? It's going to be a negative value, something here. So he just said, all right, let's put a negative there. Now my calculation gives me a positive number. That's much better. Scientists don't like negatives because it's easy for them to get lost in the calculations. So this expression, Sorensen identified as little p, big H. Okay. If you write on your paper big P, big H, that's wrong. If you write big P, little h, that's wrong. It has to be small p, big H in order to represent pH. And it's just a calculation. The negative log of the hydrogen ion concentrations is pH. So if you're given hydrogen ion concentrations, calculate the pH. If you're given pH, then you can work backwards to the hydrogen ion concentration. Okay, how would you do that? Well, you would move the negative over here first. Like that. Then we'd go back to the definition of logarithms. Common log to the base 10. What does this mean? This number is the power of 10 that is that number. So that means that hydrogen ions would be 10 to the minus pH. Okay, that's often called the anti-log. But that's how you do the calculations. significant figures. All right, let's take an example. Say we have hydrogen ion concentration of 7.2 times 10 to the -3 molar. Okay. Then we do the formula says this. That we take the log of that value, 7.2 exponent -3. Let's see, 7.2. There we go. Take the log of that number and then change the sign. This is 2.142668. Okay. How many significant figures does the pH have based upon this one? The rule is the number of significant figures, here is 2, is the number of decimal places in the pH. So we chop it off here, and that means 2.14. Okay? Now, if we go backwards, we change this sign, right? We take the sign, this negative sign. If this is negative log of the hydrogen ion concentration equals 2.14, then we say the log of hydrogen ions equals negative 2.14. And then hydrogen ion concentration equals 10 to the -2.14. So I just go backwards. 2.14, change the sign, and do 10 to the x on your calculator. And this says 7.24436 times 10 to the -3. Now, how many significant figures can I keep? I can keep the number of significant figures is the number of decimal points in the pH. So I've got 2 here. I can keep 2 here. That means these are gone. And it's 7.2 times 10 to the -3, just like that. Okay? That's how you keep track of your significant figures in pH calculations. Okay, we mentioned earlier. Let's clear the board and go back and put some of that information back up on the board. All right, what did we say neutral was? Neutral is hydrogen ions equal to hydroxide ions. Acid is hydrogen ions greater than hydroxyl ions. And base is hydrogen ions less than hydroxide. Okay? If we are talking in terms of pH, we'll go back to the equation where water becomes hydrogen ions and hydroxyl ions. And then the K W here is 10 to the -14 equals H plus, let's see, plus times OH minus. Okay. If this is pure water and we know it's neutral and it dissociates, it ionizes, what are these concentrations going to be? The only thing that these can be is 10 to the -7th molar times 10 to the -7th molar. That's the only way it can happen, because 10 to the -7th and 10 to the -7th is 10 to the -14. Okay. So we know the concentrations. What does that do in terms of pH? Well, either one of them, if we take negative log of 10 to the minus 7, what is that? Well, the power of 10 that gives you that value is 7. Well, minus 7, then we take the minus of it. So the pH here equals 7. Okay, that's neutral at 25 degrees. Just for argument's sake, what would happen to the concentration of hydrogen and hydroxide ions if we increase the temperature? If you increase the temperature of the solution, you're going to get more hydrogen ions. But since they come from the same place as hydroxide, you're going to get more hydroxides. So these concentrations will increase, and the Kw will change, right? But the balance is still the same. We have equal amounts of hydrogen ions and hydroxide ions. So this condition still holds. It's just that pH at a different temperature will change. So we're going to stick to 25 degrees, right? It just simplifies the whole matter. Now, what happens if we add an acid, right? We increase this one and decrease this one by adding some hydrogen ions to the solution. Well, that increases this one and decreases this one. What does that do to this one? Nothing. Stays the same. But if this increases, say we increase it to 10 to the minus 6, right? That's an increase, isn't it? 10 to the minus 6 is greater than 10 to the minus 7. But what happens to this one? Well, it has to be equal to 10 to the minus 14 to multiply. So this has to be 10 to the minus 8. Okay? So now what's the value? Minus log of 10 to the minus 6, pH is 6. So as we become acid, the pH decreases. Okay? pH equals 7 here. This one, pH is less than 7. And we could do the same thing for the hydroxides. If we increase the hydroxide and decrease that one, say we change this to 10 to the minus 6. Minus 6, and this is 10 to the minus 8. Then we calculate pH from that one. That would be pH minus 8 would be 8. So the pH for basic solutions, oops, not 8, greater than 7. Okay? Here's a pH scale for a number of substances. All right, we drink black coffee, the pH is about 5. It's acidic. And the only reason it doesn't taste sour is you have other components in there that are moderating it on your tongue. Vinegar, right? If you put vinegar on your tongue, it's going to be very sour. Lemon juice, be very sour. Stomach acid. Stomach acid, an empty stomach with just the acid in it will be around pH 2. But if you eat an Italian meal with tomato sauce, pH is going to drop. It may even drop down to 1. Battery acid is about pH 1, right? So it's very low pH. And then 1 molar hydrochloric acid is going to be 0, right? I mean, it's just a formula. It's just a calculation, right? Negative log of the hydrogen ion concentration. So if we say negative log of what's 1 molar hydrochloric acid? 1 molar, right? So what power of 10 gives you 1? 0. Okay. So because this is a calculation, you can get negative pHs. They're not very useful, but in fact, Sorensen proposed not even using pH for anything pH greater than 14 or less than 1. All right. So let's calculate the pH for some sample problems here. Let's see. What's the pH of 1 times 10 to the minus 4 molar hydrogen ions? All right. So if we do that, pH equals negative log of 1 times 10 to the minus 4. Okay. We can simplify this because if you remember logarithms, the log of A times B is equal to the log of A plus the log of B. Remember that from math class. Well, if we separate this one out, since it's multiplied, then what's the log of 1? The log of 1 is 0, right? 10 to the 0 is 1. So we only have to deal with this one. So what's the log of 10 to the minus 4? It's minus 4 times the minus 4. That pH is 4. Okay? Well, let's see, we have 2 significant figures, so that means it's 4.00. All right, that's the first one. Let's see. Got the answer there? Yep. How about this one? 0.040 molar hydroxide. How do you get the pH out of that? Well, one way is to go back to Kw. Kw equals 10 to the minus 14. And that's equal to hydrogen ions times hydroxyl ions. So we have an equation in one unknown. We can solve for hydrogen ions. We need to take this one and divide it by that. So 1 exponent 14 like that and 0.045. And this is 2.5 times 10 to the minus 13. Now we can do pH. So pH equals negative log of 2.5 times 10 to the minus 13. And I just take the log and change the sign. And that's 2 decimal points. 12.60 pH. Okay. All right. Say the pH is 5.85. What's the hydrogen ion concentration? We looked at that earlier. This is a practical example. Remember, pH calculation is simply a mathematical formula. So if pH equals 5.85, that's also equal to negative log of hydrogen ion concentrations. So we just need to calculate 10 to the minus 5.85. And save time. That should be 1.4 times 10 minus 6. 1.4 times 10 to the minus 6. All right, we have 2 significant figures here, 2 significant figures there. And that's molar. All right. Now, since this calculation is simply a formula, it's a mathematical formula, instead of saying pH is the negative log of the hydrogen ion concentration, we can say pOH is the negative log of the hydroxyl concentration. Right? That's perfectly valid. And not only that, we know the expression for the equilibrium constant for water, which is always working in aqueous solutions. It's always there. Kw equals hydrogen ion, hydroxyl ions equals 1 times 10 to the minus 14. Let's see, let's make room here. We can also take the negative log of Kw. So the negative log of Kw equals pKw. All right? And if we take the negative log of the entire equation, now we get pH. And remember, when you take the log of A times B, it's the same as the log of A plus the log of B. So pH plus pOH. And that's equal to the negative log of this one, which is 14. And there we go. And if the solution is neutral, then this is going to be 7. This is going to be 7. 7 plus 7 is 14. Okay? All right. Well, let's see. Be consistent. 2 significant figures. Okay. Calculate pH, pOH for each of the following solutions. Well, notice pH plus pOH equals 14. So if we know for A, the pH equals 4, then the pOH equals 14 minus 4 equals 10. Okay. And if we want to know the pOH for 0.040, we just take the negative log of that. Negative log of 0.040 equals 0.040 log, change the sign, is 13.98. Okay, 13.98. Oops, I misread it, sorry. I misread that one. 0.40. Got to watch that scientific notation. What that means is if we want to calculate this is the pOH. Now, if we want to calculate the pH, we just say 14 minus 1.40. And that's 12.60. So this is an easier way to get it than the first time we did it. First time, we used this expression. And it took several steps. But if we go this route, we can calculate the pOH, subtract it from 14, and we got pH. So the pH of a solution is 5.85. What's the OH for this solution? Well, 5.85 gave us, let's see. Okay, 5.85. If we want to know calculate the pOH, right? We just say 14 minus 5.85 is equal to the POH. Which is 11.15. Oh, hydrogen ion concentration. Okay, now we have to do hydroxyl ion concentration then is equal to 10 to the minus 11.15. So I just change the sign here and go 10 to the X. 7.08. Actually 7.1 because it's only 2 decimal places. So it's 2 significant figures times 10 to the minus 12. Oops. I did something wrong. Hold on a second. 5.85 from 14, 11.15.
It should be 8.15.
Oh, excuse me. You're right. What am I thinking? And that makes this 9. There we go. All right. All right. So now we're going to move into acid-base reactions. When we're looking at equilibrium problems with acids and bases, the first thing we have to ask ourselves, what are the major species in the solution? Because if we have species that we think are there, but we take another critical look at the solution and say, they're not there, or they're such small concentrations, they don't matter. That's the first thing. What are the major species? And then we look at, with those major species, what reactions can they undergo? It's like we create this list of reactions that are possible, and then we say, which ones are reasonable? And at that point, we want to say, what type of reaction do we have? At this point, do we have an equilibrium reaction that we're interested in? Or does it essentially go to completion? Or sometimes is it both? Sometimes the problem is best solved by letting the reaction go all the way to completion and then taking those values and then go to the equilibrium expression and work our way backwards to the equilibrium concentrations of our reactants and products. And then if necessary, look for the hydrogen ion concentration and solve for pH. Depends on the question. So let's see, if we have this solution of 2 times 10 to the minus 3 molar HCl, what are the major species? Well, we know that hydrochloric acid dissociates completely. So there's not going to be any HCl left. There's going to be hydrogen ions and chloride ions and water. Okay, so what's the pH? Well, if it completely dissociates, we just have to focus on the hydrogen ion concentration, which is equal to the chloride concentration, which is equal to 2 times 10 to the minus 3, and calculate the pH as 2.70. Those are simple problems. How about the pH of 1.5 times 10 to the minus 11 molar solution of HCl? All right, go at it critically, logically. Right? Major species, hydrogen ions, chloride ions, water ions. And then we can calculate pH as 10.8. When HNO3 is added to water, a reaction takes place immediately, right? HNO3 is a strong acid, so it produces hydronium ions and nitrate ions. And essentially, no reactants are left. So if we proposed reactions, right, once we produce a major species of water, hydronium ions or hydrogen ions, and nitrate ions, why does this reaction not exist? Because HNO3 is a very strong acid. So this is a very weak base. That will not react with water. It doesn't want protons. So that reaction is not worthy of consideration. All right. Now we want to ask ourselves, what reaction controls the pH? Right? What's the dominant reaction? Remember, we always have water reacting with water makes hydronium ions and hydroxide ions in aqueous solution. That's always taking place. So we have to say, what's the major contributor to the hydrogen ion concentration or the hydronium ion concentration? Come on. There it goes. It's taking its own sweet time. So if we have 1.5 times 10 to the minus 2 molar solution of HNO3, those are the major species. There's no nitric acid left behind. It's completely dissociated. And we know that since the hydrogen ion concentration from the nitric acid is 1.5 times 10 to the minus 2, what's the competing hydrogen ion concentration? Well, water by itself produces a hydrogen ion concentration of 7 times, 1 times 10 to the minus 7, right? So who wins? Right? This is from water, and this is from HNO3, right? Nitric acid wins. So we just take the nitric acid concentration, calculate the pH. Okay, this is step-by-step. List the major species. Choose the ones that produce hydrogen ions and write the balanced equation for the reactions, like I did here. Well, actually, I skipped that step and actually put the values up there. Using the values of equilibrium constants for the reaction, you have written decide which equilibrium will dominate in producing hydrogen ions. So we could also look at it in those terms. This Kw equals 10 to the minus 14. This Ka is infinity. So which one's bigger? That one, of course. Then you write the equilibrium expression for the dominant equilibrium. Then here's where we go to the ice table. You want to know the initial concentrations of the species, define the change, and then your unknown, and solve for your unknown, just like we did any equilibrium calculation. You try to solve the equation so that your answer is in terms of the hydrogen ion concentration, because more often than not, you're going to be asked, what's the pH? If not, then you have to complete the calculation to give you the unknown that you're looking for. And then if you have to make any assumptions, like if you have to say, all right, if it's a very weak acid, then the change is going to be almost negligible, and we can do away with one of the X's, the unknowns, and make that assumption. That eliminates the quadratic problem. And then use the 5% rule to see if you got close. Otherwise, go to the method of approximation, the successive approximations, and get closer to the real value. All right. So here we have a weak acid, hydrocyanic acid, with its Ka of 10 to the minus 10th, like we saw before. And we've made a solution, an aqueous solution of 0.8 molar HCN. All right. What are the major species? Well, since the Ka is so small, the major species are going to be hydrocyanic acid and water. A major species is not going to be hydrogen ions from either the HCN or the water, right? Because water has a 10 to the minus 14, HCN has 10 to the minus 10. Very small amounts of hydrogen ions. They're not major species. Okay? That's why they're not major species, because of their K values. So which reaction would actually control the pH? Well, the one with the largest Ka produces the most hydrogen ions, or hydronium ions. So the controlling reaction is HCN by an order of magnitude of almost 4, right? Order of magnitude is powers of 10. So if we have a difference of 4 orders of magnitude, that's a factor of 10,000. So we can say that hydrocyanic acid is the controlling acid for the pH. Okay. So that's as far as we're going to take that one. Now we're going to switch to determining the pH of a 0.5 molar aqueous solution of the weak acid HF. HF has a Ka of 10 to the minus 4. All right, so our major species should be HF and water. So the HF reaction would produce hydrogen ions. 10 to the minus 4 is its K. Water is a competing reaction, 10 to the minus 14. That's 10 orders of magnitude. So the controlling reaction is HF, right? So we put our reaction up there as HF and water is in equilibrium with hydronium ions plus F minus. These are aqueous. Okay. So what's the initial concentration here? 0.50 molar. That one doesn't count, right? Because it's pure liquid, right? How much of this do we have at the beginning? Well, approximately 0. And all we need to know is that it's going to drive the reaction toward the right. So we assume that's 0. What's the change? Well, we're going to lose some of this. We're going to produce some of that and some of that, right? Because it's moving that direction. And the ratio is 1 to 1 to 1. This is typical for acid dissociations or base dissociations. Is 1 to 1 to 1 reaction ratios, because we only do one proton at a time. Okay, so what do we have here? At equilibrium, we have 0.50 minus X. Here we have X. Here we have X. Okay, and the Ka equals 7.2 times 10 to the minus 10, is it? No, 4, excuse me. 10 to the minus 4. And that's equal to X times X divided by 0.5 minus X. So we have X times X over 0.50 minus X. Okay. So what does that give us? Well, it gives us the potential for a quadratic equation. But since Ka is so small, these values are going to be very small. We can say that this is approximately x squared over 0.50. And that's equal to 7.2 times 10 to the minus 4. So all I need to do is multiply this one times that one, take the square root to find out what x is. Let's see. I think we've got part of that in here already, don't we? Yep, there it is. Okay, there's our expression. And we're assuming that x is so small, it's a lot smaller than 0.5. And then if we solve for x, let's see if I get the same number. 7.2 exponent minus 4 and 0.5, and take the square root, and I get 1.9 times 10 to the minus 2 molar for x. Well, 897. Let's see. Two significant figures. That's really all we're allowed. Okay, so what was the question? Solve for pH? Well, first of all, does it obey the 5% rule? Right? In order to do that, now that's not part of the slide, but let's check ourselves just to be sure. If we put this x in here, right? Actually, if we put x in here, here, and here, and compare it to that, it needs to be within 5% of that value. So if we say this, 1.9 times 10 to the minus 2 squared divided by 0.50 minus 1.9 times 10 to the minus 2. What would that be equal to? That's, let's see, 1.9 exponent minus 2. I'm going to square that. And then I'm going to say 0.5 minus 1.9, 10 minus 2, and divide that into that value. So that's 7.5 times 10 to the minus 4. Okay. So is that within 7.2? So how do we tell, right? It's like percent accuracy. 7.5 minus 7.2 times 10 to the minus 4 divided by 7.2 times 10 to the minus 4 times 100. So let's say 7.2 exponent per minus, and then 7.2 exponent minus 4 divided times 100. And I get 4.2%. Okay. So this value, the assumption we made, gave us a value within 5%. So we can say that's valid. And then if we take the negative log of this value, we get a pH of 1.72. Okay, so we solved the pH for this HF solution. Now, if we change the concentration from 0.5 to something else, we're going to get a different pH. Let's see. Oh, okay. So I did have a slide on that one. Only this slide uses more significant figures than I did. So it's going to be slightly different, 3.9% instead of 4.2. But we're within 5%. Okay. Here's another concept that can be difficult to wrap your brains around, but it's often very useful. And we have several problems in our review documents that use the concept to solve the problems. This is percent dissociation, or percent, actually it should be percent ionization for acids, percent dissociation for bases. So it depends on which one you're talking about. And it simply means the amount that is dissociated, in other words, if it's an acid, we're comparing this amount to that amount. So we say this divided by this times 100. That's the percent dissociated. The strange thing about this is that as the for weak acids, I should say, for weak acids, as we dilute, as we become less concentrated, as this one goes down right here, this concentration, this value goes up. Now, that doesn't mean we have more conjugate base. It just means the ratio goes up. Okay, so you may have less of this in solution, but the dissociation by percentage goes up. All right. So here's a problem where we're given this data. We have an 8 molar solution of formic acid, and we're told that it's 0.47% ionized in water. What's the Ka value? So we set up our equation where HCHO2 dissociates into hydrogen ions and CHO2 minus ion. So we're using a simplified version of this equation. So we have initial, change, and equilibrium. We're starting off with 8 molar, correct? And we essentially have nothing here and nothing here. And we're saying that the percent dissociation is 0.47%. So what does that mean? That means in decimal terms, 0.47%, 0.47% is the same as multiplying by 0.0047. Okay? So that's why we multiplied this one times 8, and this is minus 8 times 0.0047. Okay. And if we carry this calculation out and then subtract it from 8, we get 7.9624 molar. What we're going to get on this side, since it's dissociated, it produces the same amount of this over here, which is, this is just going to be a plus that amount, plus that amount. And we get 3.76 times 10 to the minus 2. These are all molar. Okay, so what would the equilibrium expression be? It would be the concentration of H plus times the concentration of the formate ion divided by the undissociated formic acid molecule. Put those values in, and we should get, excuse me, come on, there, 1.78 times 10 to the minus 4. That's for 0.47% ionization. Okay. Now, what if we decrease the concentration? Oh, and the pH, let's see, calculate the pH. We just need the hydrogen ion concentration, 3.76 times 10 to the minus 2. Take the negative log, and we get a pH of 1.42. So this pH is 1.42. There we go. Okay, so now what if we decrease the concentration to 4 molar? What's going to happen to Ka for 4 molar solution should be, well, the Ka is going to be the same, right? Ka, it's a constant, right? So trick question. It's going to be the same. The value of Ka is going to be the same. But what will happen to the percent ionization? The percent ionization should increase. So how do we calculate that? Or does it even ask us to? No, we're going to take a generic and go. But we could say, all right, suppose we put 4 molar in here and we make this X, our unknown X, right? Then we would have minus 4 times X, and this would be plus 4 times X and 4 times X. Bring those down here. Put them into our equation. Since this is exactly the same, then we would solve this equation for X and find out what the percent dissociation is, and it should be a higher number. It should be a larger number than that. But on this slide, we're going to go generic and try to explain in generic terms why the percent ionization is higher as the concentration decreases. Okay, so we have, let me see. Am I getting close to the end? Or am I going to have to pick it up again? Yeah, probably not going to make the end of this chapter. We'll have to pick it up on Thursday and finish chapter 14 and then get 15. So I don't have to rush. Okay, so generically speaking, if we have an acid, it dissociates into hydrogen ions and conjugate base. And there's the Ka expression. Okay, so if the so for a very small value of Ka, we're going to get an expression where we have the initial concentration minus some value X. So this is where we do the assumption, where X is very small. So what we're saying is that the initial concentration is still going to be the same as HA. And the hydrogen ion concentration is equal to the conjugate base concentration, which is our unknown, right? So here we're working in this region right here. And that's the initial concentration conditioned for Ka, right? We have this one times this one divided by this one. And if this is very small, then it's essentially going to be the initial concentration of the undissociated acid. Okay. Now, what happens if we dilute the initial concentration so that now it's 1/10 as concentrated? So what does that do to the values in that equation? That's what we're looking at next, right? If the new values are actually 1/10, then X divided by 10, we've stressed the system by adding water, reducing the concentration. Which way will the reaction move? Le Chatelier says the reaction is going to move toward the lower concentration. So we added water to dilute it. It's going to move to the right and produce more hydrogen ions. Right? So in order to quantify this, we calculate Q. Right? So now instead of X, we have X divided by 10. We've diluted it 1/10. We've also diluted the original by 1/10. So we can factor out 1/10 and then the Q is going to be 1/10 of Ka, right? Notice that X times X divided by HA is K. So that expression becomes 1/10 times Ka. So if Q is 1/10 of Ka, it's much less than Ka, which way is the reaction going to go? We know that if Q is less than K, that means the numerator is too small. So we're going to move to the right. That drives the reaction to the right. Right? And if we do that, that produces more of this compared to the original, and the percent dissociation goes up. It goes up, in this case, by a large amount. Okay. So now the pH of 4 molar formic acid solution should be, well, the percent dissociation caused it to move this way, but we diluted everything, right? We diluted everything. In this case, we diluted it by 2. So in order to establish equilibrium, it is going to move to the right, but it's not going to move to the right enough to increase the hydrogen ion concentration. It's still going to be lower than it was before, but not linearly lower. So the pH is going to be, should be higher than it is for the 8 molar, right? Because we've diluted it. And diluting the hydrogen ion concentration drives the pH higher. It's counterintuitive, I'll grant you that. All right. So if we do the calculation, right, we set it up like this, do the calculation, then we find out that the percent dissociation is 0.67 and the pH is 1.57 instead of 1.42. So the pH has increased some. Okay. Let's clear the board. All right. Now we're going to shift and talk about bases exclusively for a little bit. Remember, Arrhenius said that bases produce hydroxide ions from the molecule itself. You have to have a hydroxide in the molecule, like sodium hydroxide, barium hydroxide, potassium hydroxide, whatever. It has to be there in the molecule to be an Arrhenius base. Whereas Bronsted simply says that our base is a proton acceptor. We also know that basic solutions at 25 degrees C are greater than 7 pH. So what's the pH of a 1.1 times 10 to the minus 3 sodium hydroxide solution? Well, we know that it's going to be completely dissociated, right? And it's going to produce a hydroxide concentration of 10 to the minus 3. So we calculate the pOH, subtract that from 14, and our pH is 11. That's much simpler than going the other route. Okay, what about calcium hydroxide? Well, calcium hydroxide is slightly soluble. But if we say that its molar concentration now in solution, we guarantee it's in solution, is 10 to the minus 3, then we can calculate the pOH. But what is the OH concentration? Calcium hydroxide is this. So when it dissociates, it produces twice as much hydroxide. So that means the hydroxide concentration is actually 2 times 10 to the minus 3. pOH is 2.7 then, and the pH is 11.3. We're still basic, of course. So, if we have this equation, let's see, did I skip a step? No, I didn't, sorry. If we have this expression, so we put cyanide ions into solution, perhaps as potassium cyanide. Cyanide in solution will react with water to produce hydrocyanic acid plus hydroxide ion concentration. And the expression for Kb would be the same as always, products over reactants. Let's see. And we calculate the pH for this solution. Oh, I need to go in and fix this slide. Actually, the whole set. What's the pH of a 2 molar ammonia? If the Kb is 1.8 times 10 to the minus 5, then we say, how does ammonia act as a base? It accepts a proton from water. So the correct expression would be ammonia plus water yields ammonium plus hydroxide. That is the expression that we would use to equate to Kb, 1.8 times 10 to the minus 5. Right, so there's our expression. And going from the ICE table, the expressions are going to be very similar each time, right? We have two X's, right? Let's see. I don't know if I have time to do this. No, I don't have time. So you're going to have to trust me on this one. So we got X squared over 2 is the approximation. And then X would be 6 times 10 to the minus 3 OH. POH is that. pH is 14 minus 2.22. What's a polyprotic acid? Polyprotic is 2 or more ionizable hydrogens per molecule. For instance, this would be diprotic sulfuric acid. It's also polyprotic. This would be phosphoric acid, right? It would be triprotic or polyprotic. And for most purposes, if it's a weak polyprotic acid, for instance, this is a weak polyprotic acid. Its first dissociation is going to produce one hydrogen ion plus the H2PO4 minus ion, and it will have a Ka there. Then if we take this one, PO4 minus, dissociate that one, it's going to have HPO4 2 minus with a Ka2. And then we can take our last one, PO4 2 minus. The last hydrogen to come off produces PO4 3 minus with its K. Okay? Now, the relationship of these is that the first one is stronger than the second one, and the second one is stronger than or bigger than. This is larger than that one, and that one's larger than that one. The simple logic tells you that this is a neutral molecule. We're trying to separate a positive charge from it. Right? That takes a certain amount of effort. This one is already charged, and we're trying to separate a positive from it. That takes a lot more effort. So the equilibrium is not going to be as far to the right. And then this one is more charged. It's even less. So that's a rough explanation of why the first K is larger than the second, and the second one's larger than the third. And they're the actual values for the first, second, and third K. That's why the pH is the predominant reaction is the first one. This one determines the pH of the solution. And we check the 5% rule, and we're too big. So we got to go in and do a successive approximation. And now we find that the X is 8.27 or 28 times 10 to the minus 2. We check that one, and it's less than 1. So the second approximation got us within 5%. Now that we know what the hydrogen ion concentration is, we can calculate the pH. Based upon the rule that the first one is going to be the dominant reaction. It's going to be the dominant producer of hydrogen ions. Now, these reactions are still going to occur, but the concentrations here, here, and here are so small that they don't have no impact, essentially no impact on the hydrogen ion concentration or the pH. So the pH of the solution for 1 molar phosphoric acid is going to be 1.08 in spite of all the other reactions that take place. Now, if we want to find out what this concentration is, we have to continue with successive reactions. All right. So the first one is going to produce, well, actually, we use the results of the first one, and we get the X, which is going to be the hydrogen phosphate polyatomic ion. And that's going to give us a value. Should be in there somewhere. We eventually work our way down to a phosphate ion concentration of 10 to the minus 19th. Very, very small. And similar to the idea that in chemistry, strong versus weak has a different definition than strong and weak does in popular media. Remember, a strong acid is one that dissociates completely and produces, well, ionizes completely and produces all hydrogen ions from the available molecule. Oh, there's Ann. Okay. Similarly, the common understanding of salt is table salt. Some people might have an expanded view of it, but in chemical terms, a salt is a product. Salt is a product of an acid and a base reaction. So when you have an acid reacting with a base, and let's see who else just beeped in. Jada. Okay. That means everybody's here. Okay. When you react these, you can look at this reaction as a double replacement reaction, where the sodium and the hydrogen trade places. And that being the case, you're going to get water plus sodium and chloride. That is the chemical definition of a salt. It's a product of an acid plus a base. And it always includes the cation from the base and the anion from the acid. All right. So now that we know what to call salts in chemical terms, we can look at the salt itself and we can deduce the origins of its production. I mean, even if we purify sodium chloride from a mining source, we can still look at it in terms of where might it have come from? All right, if we say potassium chloride over here, we can deduce that it came from hydrochloric acid and potassium hydroxide. Okay. Or sodium nitrate. Sodium nitrate we can deduce that that would have come from nitric acid and sodium hydroxide. And this is useful because if you have the salt and you don't have the acid bases to deal with, what happens to a solution in terms of its pH when you add a salt, a soluble salt, to that solution? I mean, does it remain neutral as a pure water, or does it become more acidic or more basic? So we get some rules of thumb, and then I'll explain why they work. Rules of thumb are: if you have a salt that's the product of a strong base and a strong acid, like strong base, strong acid, producing this salt, that solution will be neutral. Similarly, strong acid, strong base, strong acid, strong base, these all would produce neutral solutions. If, on the other hand, you have something like this one. See, let's get these out of the way so we don't get confused. See, we're going to have a different salt because we're going to use a different acid. Suppose we use a weak acid, acetic acid, and a strong base. We're going to produce on this side the sodium acetate salt. Okay. Now, the rule of thumb would be if this is strong, a strong base, and this is a weak acid, then the solution is going to be basic. Okay. Now, that's the rule of thumb. The reason that it happens is that this weak acid produces a strong conjugate base. Okay. So what does a strong conjugate base do? A strong conjugate base like this one, C2H3O2 minus, in solution, reacting with water, has a very strong affinity for hydrogens. So it takes a hydrogen from that water and produces the weak acid plus hydroxyl. And that's where your basic solution comes from. This is the rule of thumb. This is the chemistry. If we want to do a calculation with this one, with this reaction, an equilibrium calculation, what K would we use? Right? We wouldn't use the Ka for this. We'd use the Kb for this one. Right? We learned last week that all we need is the Ka of acetic acid in this calculation, and that'll give us the Kb for that reaction. Okay. Now, another rule of thumb. Say we have a strong acid, hydrochloric acid, Okay. And we have a weak base, ammonia. What are we going to get out of that? We're going to get ammonium chloride. Now, that's not balanced yet. What we need is, let's see, we got 4 hydrogens here and we got 6 hydrogens there. So we need an extra, let's see, we've got 6 hydrogens on that side. Then we need 3 here. That means 3 chlorides. Oops, that's not going to work. Balancing this equation. All right, well, let's do it the hard way. Right? Got hydrogens, chlorides. Okay, let's break it up. So we got 4 hydrogens here, 1 chloride, 1 nitrogen. And on this side, we have 6 hydrogens. We have 1 chloride and 1 nitrogen. Okay. All right, we're going to have to start with the hydrogens because these are already balanced. So how do we get 4 and 6 to balance? Well, if we put, we've got 2 possibilities for hydrogen. We can go here, we can go here. And it looks like we've added a hydrogen here. You know, it might be more useful. I'll tell you what, let's save ourselves the trouble. What is this going to do? This is going to produce hydrogen ions and chloride ions in solution, right? Because it's strong. Reacting with this one, what we're going to do is get this one over here, like that. So in fact, this reaction won't produce any water, right? It's just going to produce ammonium chloride. And the water is everywhere. All right, this solution is going to be acidic. Okay, strong acid, weak base, acidic. Actually, what we could do, if we wanted to be consistent with the acid plus base equals water plus salt, when we put ammonia into the solution, we're going to get ammonium hydroxide, and that will complete the picture. Okay. That's so we can be consistent with our understanding of acid-base yields salt in water. Either reaction works, and it produces an acidic solution. Now, why does it produce acidic solution and not basic solution? Well, if this is a weak base, right, it's going to produce a strong acid. Right? So that gives us NH4 plus in solution with water yields NH3, which is our, this derived from a weak base. But that gives us this plus H plus or H3O plus. So that's where the acidic comes from. If we know the Kb for this one, we can calculate the Ka for that one and then conduct an equilibrium problem. But this is the rule of thumb, and this is the chemistry. All right. This table, the idea behind this table is to organize what we know about acid-base reactions and the product solutions. Right? Let's see. All right, the way this is given, take the top one, sodium chloride. When you put sodium chloride into water, you get a cation that does not react with water and an anion that does not react with water, which means that the water is still there by itself, giving us a neutral solution. On the other hand, if you have sodium fluoride, you have fluoride, which will be a strong base, will take hydrogens from water. Sodium will not react with water. So when you put these in solution, this will not react, right, with water. This one will react with water and produce the weak acid plus hydroxyl ions. That gives you a basic solution. In the other possibility where you have ammonium chloride, ammonium coming from a weak base is a strong acid. So ammonium will donate a hydrogen to water and produce an acidic solution, whereas chloride will not react with water. Now, the one that we didn't cover is, what if you get a salt that's derived from a weak acid and a weak base? In that case, you have a competition going on. Right? You have a competition where we would say, okay, in this example, aluminum sulfate. Aluminum sulfate would have 3 here and 2 there. In solution, this is going to produce aluminum 3+ ions and sulfate 2- ion. Let's see, we're going to have 2 of these and 3 of those. All right, we can look at these as, what is their potential reaction with water? Well, aluminum then could potentially react with water to produce, let's see, aluminum hydroxide, right? Let's see, that's 3. And we have extra hydrogen here. If I do, that's not working. Hold on a second. Well, will aluminum react with water? And then will sulfate react with water? Those are our 2 possibilities. So if aluminum reacts with water, we would expect it to produce aluminum hydroxide. Plus what? Aluminum's spoken for. 3 hydrogens, we only have 2 here. So if we put a 2 here and a 3 there, that gives us 6 hydrogens and 3 waters. Okay, and then we need a 2 here. So that's balanced, right? We react this one. This will take 2 hydrogens, right? 2 hydrogens. Well, actually, the weak acid part here is going to be 1 hydrogen, HSO4 minus plus OH minus. Yep. Because this is a weak acid. H2SO4 is a strong acid for the first proton. So that's why I stopped here. All right. So what we have to do is say, all right, which one is going to produce? We have to look at the conjugate acid of the weak base. Conjugate acid of the weak base here. The conjugate acid of that weak base would be well, that'd be aluminum. This is a bad example. It's difficult to make sense of this one. What you have to do is compare the Ka of the weak acid with the Kb of the base. The conjugate acid Ka. This makes it simpler. Let's go this route. The conjugate acid has a Ka, and the conjugate base has a Kb. Now, what's the conjugate acid for this reaction? Well, remember, the conjugate acid is what happens when this breaks up, right? Conjugate acid would be what can donate a proton. This can donate a proton. What can accept the proton? This can accept the proton. Okay, so you compare the K of the conjugate acid and the conjugate base. Whichever one is larger tells you if it's a Ka is larger, acidic solution. If Kb is larger, basic solution. That was not a good explanation. I suggest you read your book and see if it makes more sense. I mean, it's still comparing the Ka and the Kb is true. If the Ka is greater, then the pH is going to be less than 7. Kb is greater, it's going to be greater than 7. And that will tell you whether the solution formed from the salt is going to be acid or base. All right. Calculate the Kb values for C2H3O2 acetate ion or the cyanide ion. Well, we know how to do that, right? Let's see. Did I do it down here? Yeah. So the Kb for this one is the Kw for water divided by the Ka for the acetic acid. And the Kb for C2H3O2 minus is 10 to the minus 10. And the cyanide should be a similar calculation, is going to be 10 to the minus 5. So which one has a stronger attraction for protons from water? The cyanide ion. It is a much, excuse me, no, the acetate. The acetate should give you a, no, I had it right the first time. Cyanide is going to attract protons more strongly than the acetate ion. Okay, suppose we try to arrange this list of salts from lowest to highest pH, from acidic end to the basic end. We have two possible approaches. We can use a qualitative approach and try to deduce from their electronegativities and what we know about the strength of the acids and the bases to arrange them, and that usually works. And then the second approach is to actually look at the K values and determine whether they're acidic or basic and how strongly they are. All right, so if we have these HBr, let's see. Well, let's just put them up here as we come to them. Are there any compounds composed of ions from strong acid, strong base interactions? If strong acid and strong base interaction gives you a salt, then that one is going to be neutral. It's going to be dead center, pH 7. So if we put pH here as 7, and we say the more acidic is going to be here. Let's see, are we from lowest to highest? So we better put lowest on this side, acidic on this side. Okay. So this would be like pH 1, and this would be basic. And this would be like pH, I don't know, 13. Okay, on that continuum. Okay, so right in the middle are going to be any that have strong acid, strong base derivatives. Sodium chloride looks like a good candidate. So sodium chloride is going to be right in the middle, right? And its pH is going to be greater than anything below it and less than anything above it. Okay, so that takes care of sodium chloride. Right, that's going to be neutral. Next question. Are there any strong or moderately strong bases? We know sodium hydroxide is a strong base, so it's going to be way over here. Okay. Are there any others? Let's see. I don't see any other strong bases. Ammonia will be a basic. Now, how would it compare to the others? If this is acid versus base, then we're not talking about salts yet. We're talking about just pure acids and bases. So ammonia is going to be next door to sodium hydroxide. Okay, next we're going to look at, are there any acids? We missed that. Okay, we're filling in the salt side first. I would go to the acids next. Do you have any strong acids? HBr is a very strong acid. How about HF? It's an acid, but it's weaker than HBr. Okay. So that takes care of 1, 2, 3, 4, 5. 5 of them. Who do we have left? Sodium cyanide and ammonium chloride. That's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So which one did I miss? Hydrocyanic acid. It's going to be a weaker acid than HF. Okay. So now we have to position these two. All right. That's where this next question comes in. Are there any composed of weak acid, strong base interactions? Strong base, weak acid. So this is going to be basic. Yeah, this is going to be basic. Sodium cyanide. And that leaves only ammonium chloride, which should go here. Weak base, strong acid. So this one's going to be NH4Cl. That should be our order. Okay. There. And we did that one already. And then we get ammonium chloride. We positioned that one. All right. So we got our numbers are 1, 2, HF, yes. 3, hydrocyanic, yes. 4, ammonium chloride. Yes. 5, sodium chloride. 6, sodium cyanide. Yes. 7, ammonia. Yes. And the last one, sodium hydroxide. Okay. So that was, put these in order, lowest pH to highest pH, using what we know about their behavior, right? What we know about their general, the general behavior. Okay. Now, if we do this in terms of Ka and Kb values, right? The Ka values are going to be useful for this side and this side, and then competition for these. We know that one's going to be neutral. There's no question about that. But the Ka for HBr is infinity, right? Ka, essentially infinity. HF is 10 to the minus 4. Okay? HCN is 10 to the minus 10, 6.2 times 10 to the minus 10. And ammonium chloride, all right, we're using Ka for that one. Actually, it would only be K because we're not looking at an acid there. We're looking at a salt. So that's kind of on the edge of credibility. Ammonium and chloride together produce a Ka. And it's just, let's see. Looks like it's smaller. Okay, I see what we're getting at. They're saying the Ka is for the ammonium. And the chloride would be, no, that doesn't make any sense either. So this is actually a K value. This is Ka. This is actually a K value. K equals 5.6 times 10 to the minus 10. So that means this one is more acidic than this one because that's larger. Okay, that's kind of misleading because it's not really a Ka. You're looking at a salt. Now, if we look at the Kb for sodium cyanide, similarly, it's 1.6 10 to the minus 5. That's a K. But the Kb for ammonia is 1.8 times 10 to the minus 5. And then sodium hydroxide is infinity. Okay, so with these exceptions, where this is actually a K value and a K value, the rest are Kas and Kbs. But you can still compare the values and say, and put them in order. Right? But still, the sequence of steps still holds. Okay, let's see. If we're looking at 0.3 molar solution of sodium fluoride, the Ka of HF is 7.2 times 10 to the minus 4. All right, we're going back to the equilibrium steps. What are the major species? First of all, is this a soluble salt? Right? Think back to the first semester where we had our solubility chart. All alkaline metal salts are soluble. Sodium fluoride is definitely soluble. An aqueous solution produces sodium ions plus fluoride ion. So what are the major species? Major species are sodium ions, fluoride ions, and water. There we go. Now, so if we're going to look at what are the possible reactions that can occur? Sodium's not going to react with water, and it's not going to react with fluoride to give you sodium fluoride because it's completely soluble. So this one is a spectator. Now we have this possibility. We have F minus plus water, right, yields HF plus OH minus. That's the possible reaction. But we're only given the Ka for HF. So what's the Kb for F minus? The Kb is equal to 7.2 10 to the minus 4. One times 10 to the minus 14. There you go. I'm going to go ahead and calculate that because we may or may not need it. It depends on how far this question goes. 7.2 exponent minus 4. So the Kb for that anion is 1.4 times 10 to the minus 11. Okay. Why isn't sodium fluoride considered a major species? Because it's completely soluble. It is not reconstituted in solution. What are the possibilities for dominant reactions? Well, we wrote one already. This one's possible. Right? And then we can speculate on the rest. Water and water, yeah, definitely. Right? The water will react with itself or it's with its neighbor and produce hydronium ions and hydroxyls. Yep, that definitely happens. Sodium will not react with water. Why? Because sodium hydroxide is completely soluble. Sodium ions will not react with water. All right, so we cancel that one. Sodium will not react with a fluoride ion because it's completely soluble. All right, so we throw that one out. So we have these two competing reactions. The fluoride ion with water and water with itself. So how do we know which one controls the pH? Well, we look at this one, and we calculated a Kb for that one. Okay. Then we look at this one, and we know what the value is for that one. 1 times 10 to the minus 14 is for the competing reaction. So who wins? 10 to the minus 14 or 10 to the minus 11? 10 to the minus 11 is 3 orders of magnitude stronger than 10 to the minus 14. All right. Well, they kept 2 more decimal places. That's fine. And we compare that with water. We find that the Kb for a fluoride ion is much, much stronger attractant for hydrogen ions than water is for itself. So the controlling reaction is the fluoride ion with water. Right? That's as far as we're going to take that problem. Now we're going to try to solve a problem using that method. Only this time we've got hydrogen cyanide. Excuse me, we have sodium cyanide in solution at 0.75 molar. So if we've got, put what we have up here, 0.75 molar sodium, cyanide. There we go. So in solution, what is this going to do? This is going to, in aqueous solution, so all sodium salts are soluble. So this is going to produce only sodium ions and cyanide ion. Okay. Now we know that this is derived from cyanic acid, hydrocyanic acid, excuse me. So, and sodium is not going to react. It's a spectator. So we know that this is one possible reaction. It's going after water. And it's going to be in equilibrium with hydrocyanic acid plus OH minus. Okay. Now we know the Ka for HCN. What's the Kb? For this reaction, Kb then is going to be 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 10. (6.2) 10 to the minus 10. And that gives us 1.61 times 10 to the minus 5. Right? Go through the same steps as before. What are the major species? Sodium, cyanide, and water. We consider these reactions. We throw out the ones that don't make any sense. Right? Sodium doesn't react with anything. And then we compare. We have two left over that have to be that are in competition. Which one is the major? Well, we look at 1.6 times 10 to the minus 5 is Kb for the cyanide ion. For water, it's 10 to the minus 14. So the cyanide ion wins. And that's the reaction that we use. 1.6 times 10 to the minus 5. Let's put it over here. 1.6 times 10 to the minus 5 equals that over this. Okay. And then if we use our ICE method, by the way, what's the question? Solve for the pH. Okay. Solve for the pH. There and there. So we start off with 0.75 molar. Why? Because this is completely soluble. 1 to 1, 0.75 molar compound is 0.75 molar cyanide ion. So that's where we start. And this is essentially 0. So what happens? Well, the reaction has to move this direction because those are 0. So we lose some here and we gain the same amount here. So now we have 0.75 minus X, X, and X. Okay, if we put that into our expression, 1.6 times 10 to the minus 5 equals HCnOH on top is X and X. And on the bottom, we have 0.75 minus X. Okay. Now, one of the problem here is that we're going to end up with a quadratic. Right? So can we tell from this value here, is X going to be significant? If that tells you that the reaction is heavily weighted to this side, then X is going to be very small. And we can approximate this equation as 1.6 times 10 to the minus 5 over X squared divided by 0.75. So all I have to do is multiply 1.6 times 10 to the minus 5 times 0.75 and take the square root. So I get 3.5 times 10 to the minus 3. And that's molar in OH. This is molar OH. Now, to be safe, we should take this value and put it in here and see how close it is to this value right here. We can do that pretty quick. I'm going to take that value. It's already in my calculator. So I'm going to square it. Right? And then I'm going to take 0.75, enter, and 3.5 exponent minus 3. And it's going to go in here, subtract that value from this one, and then divide it into the previous one. I get 1.6 times 10 to the minus 5. So we're well within 5%. So we can go with this value as the hydroxide ion concentration. But what was the question? Question was, what is the pH? Right? And all we have is hydroxide ions. So if X is the hydroxide ion concentration, we ought to determine the pOH. Right? Negative log of 3.5 times 10 to the minus 3 is equal to what? 3.5 exponent negative 3. Well, they're using 4.6. That's okay. Let's see how close we get to their number. Log, change the sign. So I get 2.5. They got 2.46. Well, actually, two significant figures gives you 2 decimal places. So I should be 2.46. There we go. 2 significant figures, 2 decimal places. pOH is 2.46. What is pH? Is 14 minus 2.46. Which is 11.54. That's the pH. Okay. We could have gotten lost in this calculation by assuming that X was our answer, right? But X is not the answer. X is on the way to the answer, producing the molarity of the hydroxide ions. The question is the pH. Then we have to find out what is the pOH, subtract that from 14. That gives us our pH. And it's easier to assess the acidity or the basicity of a solution if you know the pH. pOH is not quite as intuitive as pH is to me. So I know 11.54 is definitely basic, it's strongly basic. Okay. So now that we have that calculation under our belt, and we're still in chapter 14. I know chapter 15 says acid-base equilibrium, but we're already in the equilibrium in chapter 14. That's another reason that I put both chapters together. Then I don't have to worry about it. We're eventually getting to equilibrium if we do 2 chapters. Now, these are factors that control the acidity of binary compounds. Bond polarity, in other words, acidity. Say we have this hydrogen attached to this anion. This is acetic acid. This is the acidic proton. Those protons are locked in place. This is the only one that can go. So what we want to know is how polar is that bond? Right? The more polar the bond, which obviously means it's polar in this direction. Otherwise, we can't get the proton off of it. It would have to be polar in that direction. This would produce negative, positive. The more polar that bond for this molecule or for any molecule, the more polar that bond between the hydrogen and the rest of the molecule, the stronger the acid, because we're making it easier to remove that proton. Right? We can take that off of here and make a like that, and that leaves the negative charge here. So that weakens the bond. The polarity weakens the bond and makes the hydrogen more available to ionize into solution. The other possibility is bond strength. What do we know about the strength of the bond? Sometimes they're related and sometimes they're not so related. But we consider both of those possibilities when we're assessing the acidity of a compound. So here's a list of halogens, acids of halogens. And we notice that if we start at the bottom, we've got iodine, then we come up in the periodic table, come up to bromine, to chlorine, to fluorine. And all of these are valid acids. We find that the strongest of those, based upon bond strength, right? If we did, let's put them up here. HF, HCl, HBr, and HI. Okay, bond strength and bond polarity. I know that's not in the chart, but we're going to put them together for our discussion. Right? We're already given, we can quantify the bond strength as kilojoules per mole. So this one is 295 kilojoules per mole. Right? 295 and then 363, 427, and 565. Okay. We know that bond polarity, fluorine has an electronegativity of 4. And hydrogen has something in the neighborhood of 2.2, I think. So what we're saying is, and the trends of the periodic table tell us that the bonds are going to be more polar this direction. So increasing polarity this way. So the most strongly polar bond is going to be this one. Okay. What we find is that we should expect the bond strength is weakest for this one. Right? Bond strength is weakest. So that means this should be the strongest acid. This should be the strongest. Based purely on bond strength. We're not talking about polarity yet. Bond strength. If this is the weakest bond strength, this the weakest bond strength, it should be the strongest acid, and then we get weaker as we go up. Okay? Until we finally get to HF, and it is a bona fide weak acid with a non-infinity K value. These are essentially all strong acids, but this is the strongest based upon bond strength. Okay. What if we look at in terms of bond polarity? We know that the electronegativities here increase as you go from bottom to top. So the polarity should increase. That means this is more polar bond. Right? That's a more polar bond. So there's a competition between bond strength and bond polarity. And the physical, the measurable evidence is that this is a weak acid. So that tells us that bond strength wins over bond polarity for this one. Bond strength is so high that that hydrogen has a difficult time exiting or ionizing from the molecule. So you have competition going on between those two. Sometimes one wins over the other. Well, it usually does. One is more effective, has more influence on the outcome than the other one does. And I think I've talked about this before. One of the reasons that this bond is so strong is due to the electronegativity of fluorine and the small size of the ion. This is a concentrated source of negative charge. And this is a very small, it's a proton. So it can get very close to the fluoride before we have interference or we have rejection of the proton by protons in the fluorine. So it get very close, and closeness in electrostatic terms means strength of bond. So that's why this bond is so strong, and the polarity has actually contributes to bond strength and not so much to the weakness of the bond for acidic purposes. All right. So now we're going to switch gears to another concept. And this has to do with acids that are formed from polyatomic ions that have oxygen in them. These are oxyacids. And what we mean by that is there's something here, and then there's at least one oxygen to which the hydrogen is attached, right? There may be other oxygens out here, and we're going to address that right now. If there's only one oxygen, then you have polarity here like that. Okay? If you have other oxygens over here, usually up to 4, then you get what's called the inductive effect. In other words, we're drawing electron density away from that oxygen, which weakens the bond. It makes it more and more polar by induction. Which means for a given X, whatever that happens to be, the more oxygens that are in the polyatomic ion, the stronger the acid. Okay? So let's see, we got some examples here, I think. If we use the ones with chlorine as our X. Remember when we were naming compounds? I put these in sequence. We have ClO3, ClO4, ClO2, and ClO there. And these are polyatomic ions. We're going to start there. This is chlorate. This is chlorite. Excuse me. This is hypo. Hypochlorite. And this is perchlorate. Okay? Now, all we have to do to make an acid out of each one of these is add a hydrogen on the front. Now we don't have the negative charge anymore. And the names become hypochloric acid, chloric acid, chlorous acid, and hypochlorous acid. Okay? Now the K values are listed here in that table. The K values, the Ka's here, increase in that direction. Which means what? Which means stronger acidity. The higher the K value, the stronger the acid. Right? The perchloric acid is extremely strong. It has a K value that's greater than 10 to the 7th. The chlorate is a little weaker. Right? It's got one less oxygen. It's a little weaker. It's about Ka=1. Then the chlorous acid is even weaker than that. It's in the neighborhood of 10 to the minus 2. Hypochlorous acid, 10 to the minus 8. Now, there are other examples, but this illustrates the point. As you add oxygens, everything else being the same, add oxygens, you get a stronger acid. Now, for this one, we're still talking about an oxyacid, but we're now, instead of this, we're putting an oxygen in between. Okay, that's the change. Actually, we left HF out because this is unstable. It will decompose. All right, so we have to throw that one out. We can't use that one. But we can look at the chloride, bromide, and iodide versions. What we see is the electronegativity is increasing this way. Right? Electronegativity, En, increase. The Ka for the acid then is also going to increase, going that direction. It's just the opposite. When you stick an oxygen in the middle, you get the increase in electronegativity and you get the increase in acidity, or the K value increases. So this is going to be a stronger acid than this one and stronger acid than that one. It's just the opposite trend if you don't have the oxygen. Yeah, HOF decomposes. We put HOCH3 in there, which is what? Flip it around, that's methanol. Methanol has an extremely high Ka. Excuse me, extremely small Ka. My world is turned upside down. Okay, continuing with oxides now. Now we're not talking about the oxyacids. Instead, we're going to talk about oxides of nonmetals versus metals. Okay. The oxides of nonmetals. Let's see, let's put a heading up here. Oxides of nonmetals versus metals. Okay. Our examples here are SO2, NO2, and CO2. And we'll get metals in a minute. These oxides, what happens to them when you dissolve them in water? When you dissolve these in water, they react to produce an acidic solution. And there's one example where you dissolve sulfur dioxide in water, you get sulfurous acid. Okay, so what does that look like when we dissolve it in water? Well, it's going to take a proton and a trying to put these in terms that make sense. Here we have again this inductive effect. When SO2, for instance, reacts with water and produces a molecule where the hydrogen is bound not to the sulfur, when we write it like this, it looks like it's bound to the sulfur. But when we write the Lewis structure, let's do that. We have 2 electrons. Sulfur valence would be 4, 6, and then 18. So we have 26 electrons. Sulfur is going to be in the middle. So we have 3 oxygens, and we have 2 hydrogens. Okay, 2, 4, 6, 8, 10. Right, that's 16. Right, 2, 4, 6, 8, 10, 12, 14, 16. We've used them all up. Okay. So what we have is sulfur has exceeded the octet, which it can do. Sulfur is in the 3rd period. It has access to d orbitals, so it can exceed the octet. But we need to make octets for our oxygens, right? The duets for the hydrogen. Actually, that's not right. I messed that one up royally. What we have is like that. Now let's count up our electrons to be sure I didn't mess up. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Need 4 more. So where do they go? Well, let's see. There. So 2, 4, 6, 8, that one also has an octet. We need to put 2 up here to give that an octet. And now sulfur exceeds the octet by 2. 2, 4, 6, 8, 10. Okay, the point is that these hydrogens are attached to the oxygens, and sulfur is an electron withdrawing. It has a relatively high electronegativity. So does oxygen. So the inductive effect weakens the bonds. In addition to this one, weakens the bonds and makes these acidic. So one or the other of those, doesn't matter which, comes off first. That weakening of the bond releases that hydrogen to the solution, makes acidic solution. Now, when that happens, it leaves those electrons behind, and now we have a negative charge here and a positively charged, well, it's actually a hydronium ion, right? If we add water to it. Let's see. Water would go here and yield that. Okay. So this would give us a SO3H2S. Yes, H2SO3. This is sulfuric acid, the sulfite ion. Sulfite ion. So that weakens the bond, so we get an acidic solution. All of that can be summed up in nonmetals yield acidic aqueous solutions. Right? On the next slide, we're going to look at metal oxides. These are called acid anhydrides. In other words, anhydride means no water. So you can view this as if the sulfurous acid has been dehydrated. We remove the water from it, and what do you got left? SO2, sulfur dioxide. Or acidic oxides are always non-metal oxides. If we form oxides from metals like K2O or What's our other example? Calcium oxide. Okay, that's all right. What happens here is when those react with water, let's use calcium oxide plus water. What does that yield? Well, we get the hydroxide of the metal, calcium hydroxide. Like that. Let's see. 1, 2, 1, 2, 1, 2, 1, 2. Okay, that's fine. That's balanced. I was just checking. So this is in an aqueous solution, and the hydroxide is going to produce basic environment. This one is a lot simpler. Okay. Yeah, and once you form this compound in aqueous solution, it breaks off these hydroxides and gives you your Arrhenius base, right? The hydroxide is built into the molecule. So it simply dissociates and produces a basic solution. So non-metal oxides produce acidic solutions in aqueous, and metal oxides produce basic solutions. Dissolved in water. Okay. All right. Let's see. Did I lose somebody? 1, 2, 3, 4, 5. No, I didn't lose anybody. Yeah, I did lose somebody. Who did I lose? And Gina. There's one of the Kayleys. I lost the other Kaylee. I think she has trouble with her internet connection. All right. Up to this point, we've had the Arrhenius definition of acids and bases. We've had the Bronsted-Lowry definition. Now we're going to get the Lewis definition for acids and bases. The there she is. She's back. The Bronsted-Lowry definition is effective for any aqueous solution. It works great because we have a source of proton. The water can be a proton donor, it can be a proton acceptor. But there are some environments where the concept of proton transfer is not always valid. And that's where we have non-aqueous solutions, where we have solvents that are not aqueous. They're not proton donors or acceptors. And that usually happens in organic chemistry, in organic reactions. So we need a definition where we can continue our idea of acid-base, but in terms where the protons are not necessary. And that has to do with, rather than the protons, the electron pairs. So if we look at the Bronsted-Lowry definition of acid base, okay, so this acid reacts with water to produce hydroniums plus some anion. And the base, we would say, would be something like this. Actually, Bronsted-Lowry would be something like just the base would react with water to produce HB conjugate acid plus OH minus. Okay. If we look at this in terms of the bonds, H, A, and O, H, H, like that, like that, like that, like that. And instead of focusing on the hydrogens, we focus on the electrons. So what happens to the electrons here? This is a proton donor. So when it donates a proton to that molecule, what goes with it? Nothing, just the proton. The electrons stay behind. The electrons stay right there. So that means this is an electron pair acceptor. That's the Lewis definition of an acid. A Lewis acid is an electron pair acceptor. Now, we used Bronsted-Lowry here to bridge the gap between the two, so it helps understand what's going on. But you don't have to have protons for the Lewis acid to be defined. Anything, any reactants that accepts an electron pair is a Lewis acid. And a Lewis base is the electron pair donor. You can't have one without the other. There's always an acceptor and a donor. So in our example here, the acceptor is the aluminum 3+ ion, and the donor happens to be water. In fact, 6 waters are going to be bound to aluminum. And since waters are all neutral, we didn't neutralize the charge, that ion is now still 3+. Only we have the Lewis base, or the donor, is water. And notice that water makes a good Lewis base because it has 2 lone pairs of electrons, right? And it has donated those electrons to aluminum to form the bond. Okay. So this table is designed to draw comparisons between Arrhenius, Bronsted-Lowry, and Lewis. All right. So this is just a reminder, when you're looking at acid-base equilibrium problems, what are the major species? Now, we haven't talked about this yet. We're going to get into it, chapter 15. Does the reaction go to completion, or is it only partially? Does it only go partially? And we're talking about equilibrium. So then we have to decide which equilibrium dominates. So we compare their equilibrium constants to determine which one is the dominant one. All right, so that's chapter 14.